it's a pleasure to introduce Sarai Hernandez-Torres from Technion in Israel, who is going to talk about time constant of finitary random interlacements.
Thank you very much. I'm very excited to be here. Yes, this is a joint work with Eviatar Prokashia and Ron Rosendahl, and we're all in the Technion in Israel. And well, this is going to be a talk about some processes of killed random walks. So just to be sure that we are on the same page, let me say what I mean by a killed random walk. And here I'm always working on set D in dimension at least 3. And I have a simple random walk moving on set D, and it is killed after a geometric time that is independent of the random walk. So this parameter, the parameter for the killing rate is t. So the geometric variable has parameter 1 over t plus 1, so that the expected value is t. So in expectation, we see t steps, and after tau number of steps, we kill it. So what we have is an element of WF, which is a space of finite paths. And if you know random interlacements, as I think many of here do, you kind of expect what's going to happen here. So I have this space of finite paths, and I will consider a Poisson point process on WF product the positive reals. The positive reals are going to define a level. So if I just look at this window and I start to look at time 0, then this indicates the first level at which I see some kill random walk appearing on my window, and I will see more and more walks as I increase my level. And let's say that I pick a level U, and then I want to look at the graph, which is defined by all the edges traversed by my random walk paths. So, well, of course, this Poisson point process is defined by some intensity measure. And here I'm being a little bit mysterious because I'm just saying that is some intensity measure on WF that depends on this parameter T. And it really is like kind of the analog construction for random interlacements. This measure comes from, it's built in terms of the capacity. So in our case, since we have these killed random walks, we have the killed capacity. So this is a Poisson point process on the product measure QT and the Lebesgue measure on the positive reals. And although I'm not saying you who is this QT, I will give another construction for this process that is very explicit. But I just want to point out that this kind of analog between finitary random interlacements and random interlacements is not only from definition, but we also have a convergence that this was proved independently in, well, it was added in an appendix on this paper of Louis Bowen where finitary random interlacements were introduced. And it was also proved in a PhD thesis. So it says that we have weak convergence of the finitary random interlacement of level U and killing parameter T to the random interlacement at level TD to DU. And this, well, this is a little bit strange and annoying because I will have to carry a 2D everywhere, but it's essentially just what is the degree of the vertex. So this is as T goes to infinity. And another thing that I want to point out is that the graph on which I'm going to work is kind of a bond percolation. So I'm taking really the edges that are traversed. So another alternative is that we do some sort of side percolation, and then we take all the vertices that are between nearest neighbors. But if we work in this graph, we would get stronger results because, well, the chemical distance here is smaller, because that's what I'm going to look at, the chemical distance. So as I promised, I'll give you a second construction of the finitary random interlacement. And this is really the reason why we can do stuff here, because we can have this very explicit way of looking that is not available in, the same way in the random interlacement. So now we start from scratch. We have set D, and for each vertex, I have these elements that are all independent between each other. So I have a Poisson random variable with parameter this my intensity level times the killing rate. And this NX indicates the number of random walks that are starting at that vertex X. And I have my kill random walks ready to grow in my graph. So let's say that I have my same window, and these points indicate that I got value 1 for NX, and in all these other vertices, I got value 0. So at these vertices, I will have for each one of them one independent simple random walk that is killed after some geometric time. And then I see my graph. And everything is very nice, except for a very annoying detail. And is that, let's say that I just want to know how my finitary random interlacement looks on a box. And I say, okay, well, I will just grow my random walk paths from each vertex. But it may happen that I have some path coming from far. Like, it's possible that we have this events that happen with small probability, but are going to happen. I get a very, very long random walk that comes from somewhere else and enters into my box. And as I mentioned, I'm interested in the chemical distance. So these kind of paths are relevant for what we're going to do. So let's keep that in mind. And something that is nice from this construction is that it gives a very clear picture of what happens as we increase and decrease T. So the Poisson point process construction is very nice for increasing and decreasing U, because that essentially is a definition. But for T, this is the right way to look at the process. So when we increase T, so let me show you first the previous one. This is, I have some T, and then I increase it. So what happened is that one walk disappeared, but some paths become larger. And the thing is that I can couple these Poisson random variables and these geometric random variables in a way that as I increase T, then this parameter becomes smaller, but these two parameters become smaller. So what I can see is that the number of random walks that are starting at each vertex is going to decrease. So some walks are going to disappear, but some paths are going to grow larger. So what effectively happens is that there is no monotonicity, because there is really these different ways in that my graph can reconnect again by taking a longer path. So if I decrease, then it's not clear which one is going to give me a larger graph. But we are lucky, that it is not monotone, because it means that this is interesting and we can really study it because there is a phase transition. So there exists a unique infinite cluster. So I can really look at these asymptotic properties of the chemical distance of these infinite connected components that I mark here in red. So let me be precise what I mean by this chemical distance. So I denote by this curly Fi with its parameter ut, this unique infinite cluster or connected component. And every time that I have a vertex X, I denote by a bracket X, the closest vertex to this infinite connected component. And then the distance in the finitary random interlacement between X and Y is, well, the smallest length of the path that connects the corresponding bracket X, bracket Y. So this is, well, the chemical distance, you can also define it as the graph distance or the intrinsic distance. Today, I'm calling it chemical distance. And for the finitary random interlacement, it was proved by Kai, Hang, Jie, and Sheng that if you have U larger, some level U, then there is a parameter T, a Killing parameter large enough so that your chemical distance is comparable to the Euclidean distance. So here I have T2 because I say that T1 is the critical parameter for the existence of the connected component. So in a nicer world, a nicer theorem would be that this is just enough T1. But, well, we need more properties for our graph to guarantee this statement. And we'll see T2 again by the end of the talk. But here I want to point out that this is a second critical parameter for which we can say something about the connectivity of the finitary random interlacement. And then with high probability, the chemical distance is bounded by above, by the L1 distance. And of course, well, the other bound is trivial because you cannot go faster than ZD. So what we are going to look today is the time constant. So I'm taking the normalized chemical distance and its limit out by Kingsman subadditive ergodic theorem. This exists, convergence in almost surely and in L1, and well, it is a constant. And this is really then it defines a norm that corresponds to the ball of the shape theorem for this model. So we want to understand that norm. And the theorem, as promised on the continuity of the time constant, is this continuity that should appear soon, but it seems that it's frozen. I think it froze, right? Let me stop and share again. It has happened before. I apologize. Okay, so this is the theorem of today. So I have here the definition of the time constant. And again, this is for T larger than the second critical parameter. And if we are on this right domain, then the time constant is continuous as a function of U and T. So of course, this is not the first time that the time constant has been considered. Really, the name of time constant comes from first passage percolation. So in a series of papers of Cox and Kesten, it was proved the continuity. So the continuity refers to if I have a distribution of the passage times and this distributions converge weakly, then the corresponding time constants converge as well. But in these papers, there is a moment condition. And sometime later, so this is from the 80s and this is from 2017, a general theorem without moment conditions was proved by Garrett, Marchand, Prakash, and Third. And in particular, if you don't have moment conditions, then you can start thinking about Bernoulli percolation, because you can take passage times to be infinite. And this is really an important precedent for what we're going to do today. So, well, it was considered, let's consider the time constant on supercritical Bernoulli percolation, and it exists in a paper of Primet and Marstrand. And the continuity, as I mentioned before, was proved in a more general context of first passage percolation. And recently there has been some interest on the regularity property. So in particular, this last result shows that for a strictly supercritical Bernoulli percolation, the time constant is Lipschitz. And let me show you in a nutshell what is the idea of the proof, because we're going to use it for our own model. But there is something that we have in percolation that we don't have in finitary random interlacements, and that is monotonicity. So if can
I ask you a question?
Sure.
When you say it's Lipschitz, it's respect to the distribution. So which kind of norm or distance are you using in the space of distributions?
Okay. Sorry, I didn't specify because I did didn't write it. So here for supercritical Bernoulli percolation, we change P. So it's like.
Okay, just respect to P.
Yes, with respect to P. So Lipschitz with respect to, this P, and you have the corresponding, that depends of P.
Okay.
So this is continuous. Yes. So then we only have to change P, and let's see, I have here my supercritical Bernoulli percolation at level P, but we can couple everything because all these edges are independent, so that when I see level Q, this is really a subgraph of what is a level P. So this is the kind of monotonicity that is useful, and let me show you why. So I'm going back to level P. So here it's level P. And we're interested in the geodesics. So these are the paths between, one of the possible shortest paths between these 2 points. So the arguments in actually, all these 2 papers on the continuity are based in this idea. You just see your geodesic at time P, at level P. And then you see that you're going to lose some edges when you want to decrease at level Q. So here they are a little bit shaded. So we can say that this we deleted. So now we're at level Q. So what we had as a geodesic is lost because now these are kind of disconnected paths. But what you can define is a bypass path. So kind of the idea is, what we lost before, we see the distance of this deleted path is comparable to the distance of this bypass path. So if I want to compare the geodesics between level P and level Q, they are going to be very similar because I can kind of build or reconstruct another geodesic from one level to the other. And in this case, you already, in these papers, you already have the monotonicity. So really the work goes in showing that these bypass paths are as small as you want. And in this case, all the way to showing that is Lipschitz. And to do that, the arguments require multi-scale renormalization. This is not too different for us. So for the rest of the talk, I want to just give a quick proof sketch of the main theorem of today. So I have one geodesic at level U prime to T prime, and I want to build go down to a path at level UT between the corresponding points. So the step 1 is to control the number of these deleted edges. So we want to control what is this intersection. So what doesn't appear on my finitary random interlacement when I change my parameters U and T. And the second step is building this bypass paths between the deleted edges. Very, very similar idea. So let's see. Step 1, we have to control the deleted edges. And here, what we want to say is, okay, we have the geodesics. We want to understand what edges we delete in these geodesics, but here is our problem, is that we really don't know where is a geodesic. It can be anything. There are multiple ones. And the only property that we know that occurs with high probability is that this is comparable to the chemical distance. So if this is a geodesic between, with Euclidean distance. So if I have here a geodesic between 0 and the n times the vector E1, 1, 0, 0, 0, 0, then I know that the length, so I denote here the length by these bars, is bounded by a constant that depends on the dimension and some interval around U times n. And what we're going to do is to show that for every path that satisfies this, that could be a geodesic, we're going to control the number of deleted edges that we have. So we are not going to be able to have a coupling between, I don't know, boxes or our finitary random interlacements. There's no point on trying to couple the whole space, but it is enough for our purposes to understand really what happens on these paths that have the characteristics of a geodesic. And here we have to be careful because this could be piano curves, this could be something kind of awful. And in the case of U, this is not too terrible because for U, we have the monotonicity coming from the definition of Poisson-Pin process. So it means that we only have to show one side of the inequality. And moreover, since it comes from a Poisson-Pin process, we have this inequality in distribution that our finitary random interlacement at level U plus delta T is equal in distribution to one. Okay, there should be a T here. One finitary random interlacement at level UT union, one finitary random interlacement at level delta T. So we only are interested in looking at what is the intersection of our path gamma that has these characteristics of a geodesic and a finitary random interlacement at level delta. And what we can show is that this is smaller than some very big constant, but constant depending on the dimension, on some interval around U, what we are trying to look at. So this is not uniform, this is just continuity in its very local sense. And times this function, a function of delta that goes to 0 as delta goes to 0. Actually, in this case, it's delta. And the way that we do this is that, in this case, it's simple because for a finitary random interlacement, it really behaves as in the random interlacement. So you may remember that the probability that a random interlacement intersects a finite set K is Poisson random variable given by a Poisson. So this is the same. How many kill random walks are going to intersect my trajectory? Well, this is a Poisson random variable with a parameter that depends on the capacity. And then we also have to count we are counting not only the edges on the intersection, but also like the whole length of each one of the kill random walks that intersect my geodesic. So what I get at the end is a sum of geometric random variables, and the number of that sum is a Poisson random variable. So it boils down on just doing some straightforward large deviations estimate. And that's how we can prove this one, the easy statement. For T, it's a little bit more difficult, but in a spirit is very similar idea. But instead of doing this construction of how many walks intersect my set gamma, which is the geodesic, we use this vertex construction that I showed you in the beginning. So it's how many walks start from my path gamma and then use a similar large deviation estimate. Here is not exactly the difference. Here what you get is something that dominates the difference, but it is good enough. Right now I'm being a little bit more, I'm not saying all the details because it will require more time to really to show everything. But in the spirit, it's very similar to the estimate for U. But for T, we don't have the monotonicity, so we have to show the two inequalities, but we cheated. So when we want to increase T, we use some stochastic domination. So we say, well, if you want to increase T, it's better to increase U. So we show that if you increase U by a certain amount, it stochastically dominates and increasing on T. And we show that, well, if this increase is small, this is also a little bit larger, but still small. And this stochastic domination comes from the vertex construction of the finitary random interlacement. So essentially what we do is kind of chasing the independence that we have at the time that we build this field of random walks. And that's how we use that. Well, we use that we already understand the behavior at U, and it is enough for increasing the parameter T. And well, I think that my time is almost running up, but this is how we control the amount of edges that we delete. And let's say that these red edges are the ones that are deleted. And the next step to build these bypass paths is to use a renormalization scheme that appeared in a paper of 2014 of Drewitz, Rath, and Sapochnikov. This is a general paper for a class of long-range percolation models that satisfy a set of axioms. And those axioms were verified in this paper that I mentioned before, where the authors prove that the chemical distance for the finitary random interlacement is comparable to the Euclidean distance. So then we can use that essentially says, this renormalization scheme that essentially says, these green boxes are bad. So on the green boxes, we cannot do anything about the chemical distance, but there are not too many. So part of our proof shows that if you have a path that has the behavior of a geodesic, it doesn't intersect too many bad boxes. And in those bad boxes, we just go around the perimeter of the bad box. And now that we're just in the good boxes, which is the white space, we can build our bypaths. So we can build an alternative path that doesn't increase so much the chemical distance. So this is kind of quickly what are the elements of our proof. And this is what I wanted to share with you today. Thank you very much.
Thank you, Sarai. Let's thank Sarai for this very nice talk. Now, so let's see if we have some questions from the audience.
Can I ask one?
Yeah, so sure. Daniel.
Hi, yeah, sorry, maybe you said it and I didn't catch it, but do you get a shape theorem automatically from this, and are there implications for the?
Well, the shape theorem really comes from before, where they prove that it's equivalent to the chemical distance. I don't remember if they put it as a theorem, but well, it's equivalent because once that you verify these axioms, it's one of the consequences.
Okay. All right, thanks.
So, do we have another question? Yes. So I just want to build up a little bit in Daniel's, because from my from what we started at the PhD, I remember that proving that when you vary the angle in the shape theorem, the continuity was not so easy to get, no? That was kind of...
Yeah, well, if you want to understand really the shape of the ball, you want to do something better than just continuity. You want to understand the derivative. So this is kind of a baby step in that direction in a model that is a little bit more tractable than other ones. But because of this, several ways that we have to find the graph.
Okay. Okay. Well, if there are no questions, let's thank Sarai again for this talk.
Thank you.